Hey guys, today is Friday, May 8th. Happy Friday. Today we are still learning Goal 10. This is part 2 of that lesson. Yesterday we learned how to find an antiderivative, or aka definite integral. And today we are going to actually apply that in order to approximate the area under a curve. So this is still obviously Chapter 12, Section 6, Unit 4b. Yesterday we briefly talked about the fundamental theorem of calculus. With a name like the fundamental theorem of calculus, obviously you can tell this is super important. So obviously you need to know and memorize this equation. What this equation is saying is that in order to find the area under a curve for the function f of x between the interval from a to b, so a to b, that's like a section on the x-axis, so it could be something like from -3 to 5 on the x-axis, then what you do is you take the antiderivative of the function, you plug in the b value, which is the end of the interval, and then you subtract the antiderivative evaluated at the beginning of the interval. So let me show you what this means and how you would actually apply this formula. This example says, use the fundamental theorem of calculus to find the area of the region between the graph of each function and the x-axis on the given interval. This one is y equals 4x cubed on the interval 1 to 3. So I've already graphed the function, which is a good idea. I would highly recommend sketching it out at least on your paper so that you have an idea of what you're working with. And I also already highlighted the region from 1 to 3 on the x-axis. That means that I am trying to find the area of this pink shaded region here because I need to go between the curve, I need to go between the curve, the x-axis, and these two green lines. So that region that closes off is the pink shaded region. In order to find the area of that, I need to do the definite integral on the interval from 1 to 3 of the function 4x cubed with respect to x. So that little dx just means with respect to x. So the first step is to find the antiderivative of 4x cubed. Remember, for antiderivative, we add 1 to the power and then divide by the new power. Now, typically for an antiderivative, we would put plus c. However, with a definite integral, when we are evaluating it on a certain interval, we do not need to put the plus c, and I'll explain why in a minute. But we, however, do need to include this little bar. It's a vertical line, and we include the a and b values so that we don't forget we still need to plug these in. Now we need to simplify this antiderivative. 4 over 4 reduces to 1, so this is just equal to x to the 4th, and we still have not plugged in 1 and 3, so we still put that bar there. So remember, we plug in the b value first. That's the value up here at the top. So we'll plug in the b value anywhere we see an x. Next, we subtract the antiderivative, and we evaluate the antiderivative at the a value. So remember, the a value is this value down here at the bottom. So that would be 1 to the 4th power. Now think about it. If we had done the plus c here, we would end up with plus c, and then if we distributed that negative sign, we would end up with minus c. The plus c and minus c will always cancel out in a definite integral. That's why you don't need to include them from the beginning. So don't worry about that plus c on these problems. All right, now we just need to simplify regular algebra, easy peasy stuff. 3 to the 4th power is 81. 1 to the 4th power is 1. 81 minus 1 is 80. So what this means is that the area of that pink shaded region is 80 units squared. A couple of days ago, we learned how to find the area of that region approximately using rectangles. However, this gives us an exact answer for the area of the region. Let's do another one together. So again, I've graphed out the function, and it says on the interval from 0 to 4. So I've already plotted those bounds in here too. So we are trying to find the area under the curve, above the x-axis, and between the green lines. So that leaves us with this region here. In order to find the area of this region, since it's not like a perfect square or rectangle or circle, we need to use integration. So we're going to integrate the function on the interval from 0 to 4, and our function is negative x to the fourth plus 4x plus 6, and we're integrating with respect to x. So what we need to do for integration is add 1 to the power, then divide by the new power. Whoops, I don't know where that 4 came from. Hold on. So this should be squared. Sorry about that. Same for the next term, we add 1 to the power. Technically, this is a first power of x, so when we add 1, we'll get x squared. Divide by the new power, 2. For the last term, 6, technically this is x to the 0 power. So when we add 1 to that, we get x to the first power. Divide by the new power, which is 1. And then again, remember, we don't need to include plus c on the end. We do, however, need to include this vertical bar with 0 and 4 to remind us to still evaluate this from the interval, on the interval from 0 to 4. The next step is simplify. So I like to put my coefficient in front, but for that first term, it really doesn't matter. You could have left it exactly how it was. However, for this second term, you do need to reduce it and divide this out. 4 divided by 2 is 2. And for the last term, 6 divided by 1, you must divide that out to 6. And we don't need the first power on there. Since we still have not plugged in 0 and 4, we still need that bar there to remind us that. All right, now we can go ahead, since we've simplified and found the antiderivative, now we can go ahead and plug in our a and b values. So remember, we plug in the b value, which is the number up top, first. So we'll plug in 4 wherever we see the variable x. Next, we subtract and we plug in the a value. Remember, the a value is down at the bottom. In this case, it is 0. So we have negative 1/3, and we're plugging in a 0 every time we see x. All right, now from here, it's just easy peasy math. Remember, PEMDAS, you have to do your exponents first. So we'll do 4 cubed first, that is 64, minus 2 times 16, plus, we can go ahead and multiply these together. 6 times 4 is 24, minus 0 cubed is 0, 0 squared is 0, 6 times 0 is 0. Let's keep going. Negative 1/3 times 64, that doesn't divide out evenly, so I'm just going to leave it as negative 64 over 3. 2 times 16 is 32, plus 24, and then within this parentheses, these are all multiplying out to 0, because 0 times anything is 0. Once you get good enough at this, when you see that it's a 0 plugged in and it's multiplied by every single term, you can just go ahead and put a 0 in here. But for now, I'm just writing it all out just to show you all the work. From here, it's just addition and subtraction, so I would probably just go ahead and plug this in on my calculator, and I'll see that this is equal to 34 2/3, which is about equal to 34.67. It's equal to 34.6 repeating, so we can just round that to 34.67 units squared. So what this is saying is that this highlighted region here, the area of it is exactly 34 2/3 units squared. So no longer do we have to only find an approximate area using rectangles. Now we can actually find the exact area. One other way we can use antiderivatives is for velocity. So let's do this problem together. It says, a sprinter needs to decide between starting a 100-meter race with an initial burst of speed modeled by the first function v1 of t, or by conserving her energy for more acceleration towards the end of the race modeled by v2 of t, where velocity is measured in meters per second after t seconds. Part A, use a graphing calculator to graph both velocity functions on the same screen for the interval 0 to 12. So as you can see, I already plugged these two functions in. I plugged in the first velocity function for y1, the second for y2, and I just let the x value represent t for time. So since x represents t, I know I need to change my window. A standard window is not going to work for this interval 0 to 12. Since x represents t, I know that my minimum, I need it to be a little less than 0, so I just made my x min 1 less than 0 and my x max 1 greater than 12. For my y min and max, what I was thinking, I kind of just guessed honestly, but it worked out. So you might have to guess on that and adjust it, but if you can see the full graph, then you're good. So then once you click graph, here's what you should see. The first blue function represents the first velocity function. The second represents the second velocity function, the red. So as you can see, the blue one, she's starting out with an initial burst of speed. This slope is much more dramatic on the blue curve than it is on the beginning of the red curve. However, on the blue curve, she starts to slow down. Her slope decreases, and then she starts to slow down even more. Her slope turns into a negative slope. However, on the second strategy, she continues to speed up throughout the entire race and get faster and faster. So take your guesses. Which one do you think is better? Do you think it's better for her to do an initial burst of speed at the end or at the beginning and then slow down towards the end? Or do you think it's better for her to speed up throughout the entire race? Take your guesses. Which one's going to win the race? The first thing that we need to do to figure out which strategy is better is find the position function s of t for both velocity functions. Here's what I need you to know in order to be able to solve this. So remember the other day we talked about position, velocity, acceleration. We said that velocity is the derivative of position. Next, acceleration is the derivative of velocity, aka the second derivative of position. So if we are starting with velocity now and we want to get back to position, hopefully you all realize by now that if we are starting with the derivative and trying to get back to the original function, this is where we use antiderivatives. So let's go ahead and find the antiderivative for both velocity functions so that we can get back to the position function. So we'll start with this velocity function. I already rewrote it down, copied it again, so it's easy to see here. So in order to find the to go from the velocity function to the position function, I need to integrate the velocity function. So that means find the antiderivative. So here's my function, and I'm integrating this with respect to time. That's just what that little dt means. Okay, so I need to add 1 to the power and then divide by the new power. For the second term, it's the same idea. Add 1 to the power, divide by the new power. Now, since this is talking about a certain interval, 0 to 12, we do not need to put the constant on the end. Next, for this velocity function, well, let's actually, hold on a second. We need to go back here. Let's label this. This is the position function for the first strategy. All right, let's find the next one. So in order to find the position function, we need to integrate the function. 1.2t plus 0.03 t squared with respect to t. So we add 1 to the power, divide by the new power. Same for the next term. Add 1 to the power, divide by the new power. So this is equal to the position function for the second strategy. So now we have both of our position functions. So this will tell us their position on the track at some point in time from 0 to 12 seconds. Now, let's answer the last question. How long does it take for the sprinter to finish a 100-meter race using each strategy? So the question is asking, how long does it take? So this is talking about time. So it's clearly asking us to solve for t. in one of these equations. Let's figure out, are they asking us to solve for t in the velocity equations or the position equations? It's saying that we're finishing a 100-meter race. So if we're finishing a 100-meter race, 100 meters is our position, or the sprinter's position. So let's set each position function equal to 100. Now, there are a variety of ways to solve these. I'm going to give you 2 ways. You can choose which one you like better and stick with that. But one way is to plug the left side of the equation in for y1, the right side of the equation in for y2, and then calculate on your calculator the intersection of the 2 equations, because we want to find when are these 2 equations equal. That would be when the 2 graphs intersect. So when you calculate that intersection, you should get t equals 10.34. So we'll come back to interpreting that. Let's go ahead and talk about solving the other equation. So another strategy you could use to solve this equation is to set it equal to 0 first by subtracting 100 on both sides. So we get 0 equals, I'm going to go ahead and actually divide this out to 0.6 t squared and 0.01 t cubed, just to make it a little simpler. Once we have it equal to 0, we can plug in our function to our y equals screen. Since we already used up y1 and y2, I would go ahead and plug this into y3. And since it's equal to 0, what we need to calculate on our graph is calculate zeros. If you do that correctly, you should get t equals 11.80. So let's interpret these 2 answers now. Using the first strategy, a burst of energy at the beginning, we got that it takes her 10.34, t, remember, is measured in seconds, to finish the race. Using the second strategy of speeding up throughout the race, not with an initial burst of speed, she finishes the race in 11.8 seconds. So clearly she wants to use the first strategy of a quick start, burst of speed in the beginning if she wants to do a faster time in the race. Is that what you thought? Did you think that that was the best strategy, or did you think the other one was the best strategy? Your homework for tonight over the weekend is to do your review packet. Just get it started. You don't have to have it done Monday, but get it a good start on it so you don't have a lot and you're not overwhelmed on Monday. Have a great weekend, guys. Bye.